Here's a recap of something we did in class, or at least I hope to do in class, looking at the graph of the tangent function. So again, often we're going to see y equals tan x, but I want to emphasize that really the input to a tangent function is a different kind of thing. So I'm going to call it theta. So the x-axis here is the angle theta. This is a lot like the sine and cosine sketchpad pictures I did before. And the y-axis is going to be the tangent. So how could I get the unit circle to automatically do that? Now, this is where we want to use one of these cute things. We had this other sketchpad picture that we manipulated where we discovered that if we look at an angle theta on the unit circle, if we look at the point that corresponds to that on the unit circle, its y-coordinate was the sine and its x was the cosine. That's the utterly fundamental basic stuff. The tangent we could think of as sine over cosine, but what we discovered with little similar triangles is a very nice geometric interpretation. You just keep that line going until it hits the tangent, this vertical tangent. That's not a coincidence. And this height here is exactly tangent theta. So remember, that's another way to think of tangent theta. It's this guy. I should remind you one more time, though, because something I always love to emphasize, and most books don't emphasize, and therefore most people don't remember, is that there's a simple one-word synonym for the tangent. It's the slope of this line. And how do you calculate the slope of a line? If you extend it so that the run is exactly 1 and just measure the rise, that's one way to measure the slope. So we're really measuring the slope, but we kind of got this cute trick to measure it as a height, which is going to help for this sketchpad picture. Okay, so what I did was I just extended that out to this guy, and then I just ran this over so it has the same height, but then the point here tracks the theta value. And so when theta is 0, the slope is 0, the tangent is 0. When you get to theta equals pi over 4, notice that's exactly when the slope is 1. That's really going to be really important for us because it's going to set the scale on the tangent graph. And then what's really interesting about the tangent is as that angle gets close to pi over 2, this thing goes way off the screen. It gets huge. It gets as big as you could possibly imagine, and eventually, right at pi over 2, those lines are parallel, and there's no value for tangent. But just before that, it's become incredibly, hugely positive. We say it's going to plus infinity is one way to say that. And then suddenly it comes back hugely negative. Can't even see it. And now it's coming back from negative values. And so in the second quadrant, it's negative. And then when does it zero out? It zeroes out when you get to pi. Now, of course, we saw in the sine and cosine that we can really do something cool here if we select this point and we trace it. And that'll just produce the graph of tangent automatically for us. I'm not going to worry too much about negative values because it's just going to interfere with my unit circle over there. So we get this big vertical asymptote, and then it comes back. Ooh, let me trace a few more in there. Yeah. Comes back from that vertical asymptote the other direction, which is a very common thing for vertical asymptotes. Then comes smoothly through 0. And here, what is this? 9 pi over 4. It's coming through. Oh no, 5 pi over 4. So one tricky thing here is that this line, remember, this slope, the actual point, the sine cosine point, is over here in the third quadrant. But the slope is now being positive again. And that's why the period of tangent is just pi. It's already repeated. Even though the sine cosine point is not even close to having a full revolution yet, it has done already more than one period of tangent. And here it's coming back. And now everything is back in sync at 2 pi. But the tangent says, well, you sine and cosine, you guys were lagging on me. I've done 2 full periods of my function. And sine and cosine have only done 1. That's a confusing thing, is that tangent repeats twice as often. Okay. So a summary of that would be, let's see, graph of tangent. It's still periodic, but now the period is equal to pi, not 2 pi. Vertical asymptotes, and where are they? It's wherever the line on that unit circle is vertical, and that came in at pi over 2. 3 pi over 2 is right around in here. You can see the point down here. That's the 3 pi over 2 point. And 5 pi over 2, I can just barely get to that. 5 pi over 2, that's going to be here. And so at the odd multiples of pi over 2, we're going to have vertical asymptotes. And then tangent pi over 4 equals 1 is really important because nothing else in this information has any way to set the scale of these guys. And in another video, I talk a little bit more about how to carefully plot this and also how to plot the secant function, which is kind of a natural next step.